Year 13, Chapter 8, Trigonometric Identities, Lesson 3, Expressing Trigonometric Functions in the forms r cos theta plus or minus alpha and r sine theta plus or minus alpha. So we're going to start off by considering the function y equals 2 sine x plus cos x. So that's a composition of a cosine function and a sine function. And what I want you to do is have a look at the graph of this function. Now, look at its shape. Can you see that it takes the shape of a sine or a cosine function which has been stretched and translated in some order? Now, this would suggest that this function, y equals 2 sine x plus cos x, could be expressed as some sort of trigonometric function. It could be a sine function where some sort of horizontal shift has taken place, and potentially some sort of stretch as well, because you can see the graph goes up above 1 on the y-axis. So we could have some sort of constant here as well. Now, it might not necessarily be a transformed sine function. It could be a transformed cosine function. We don't know. And we don't know whether the shift is to the left or to the right. Let's take a look at another example. Y equals 3 sine x minus 2 cos x. Again, look at the graph of the function. This takes the shape of a sine or a cosine curve. So again, the implication here is that this could be expressed as a single sine function which has been translated and stretched, or it could be a cosine function that has been translated and stretched. So bearing this in mind, we're going to make the assumption that a sum of separate sine and cosine functions can be expressed as a single trigonometric function. But of course, we have to work out what sort of translation and what type of stretch has taken place. So here's what I'm going to do. I'm going to take 3 sine theta plus 4 cos theta, and I'm going to say that this is equivalent to some sort of sine function of theta, but a translation of some kind has taken place, and a stretch of some kind has taken place. And by including these constants alpha and r, this allows us to account for the translation and the stretch, and our aim is to find the values of alpha and r. Now, we know from a previous lesson that we can then make use of the compound angle formula to expand the right-hand side. So 3 sine theta plus 4 cos theta must be equivalent to r multiplied by sine theta cos alpha plus cos theta sine alpha. And of course, we can multiply everything on the right-hand side by r. So we have r sine theta cos alpha plus r cos theta sine alpha. Now, look at both sides. We have a sine theta here, and we have a sine theta here, and we have a cos theta here, and we have a cos theta here. And what we're going to do is we're going to compare coefficients. Because this is an identity, the left-hand side and the right-hand side are identically equal. So let's start off by comparing coefficients of sine theta. Now, on the left-hand side, we have 3 sine theta, and this must be equal to, on the right-hand side, r cos alpha. So we're just comparing the coefficients of the sine theta terms on both sides, which must be equivalent. Now, what about if we compare coefficients of the cos theta term? on the left-hand side, we've got 4 cos theta, and on the right-hand side, cos theta is being multiplied by r sine alpha. And we now have a pair of equations, simultaneous equations, 2 equations, 2 unknowns, r and alpha, and there are so many nice different ways in which we can actually solve these. I'm going to show you one technique that we can use. It doesn't have to be the only way that we can do this. I'm going to square both sides. So we have 9 equals r squared cos squared alpha, and 16 equals r squared sine squared alpha. Call these 1 and 2. And if we add 1 and 2 together, we get 25 equals r squared cos squared alpha plus r squared sine squared alpha. Factorise r squared, and you will see in the brackets we have cos squared alpha plus sine squared alpha. But what do we know about cos squared alpha plus sine squared alpha? That's equivalent to 1. So this then gives me r squared equals 25. Now, for simplicity, when we're working with problems like this, we're trying to find r and alpha, if you remember, we put some conditions on r and alpha to allow for us to find the values in a unique way. So we're going to say that r has got to be greater than 0 and alpha has got to be between 0 and pi by 2 radians or 90 degrees. So if r squared equals 25, this then gives me r equals 5, as I have to take the positive root. And now I can substitute that back into either of these equations to work out the value of alpha. So we can either say that 3 is equal to 5 cos alpha, which gives me cos alpha equals 3/5. Alpha is arc cos 3/5 or 0.927 ... Alternatively, we could say that 4 is equal to 5 sine alpha. So sine alpha equals 4/5, and again, using arc sine this time, alpha equals 0.927 ... Now, another nice alternative way is to use both of these results together and to use the fact that if we take these and divide one equation by the other equation, so 4 equals r sine alpha is going to be divided by 3 equals r cos alpha. Well, r cancels and we're left with tan alpha on one side and 4/3 on the other. So we get tan alpha equals 4/3, and if we use arctan, we find that alpha equals 0.927. So plenty of different ways in which we can actually work out alpha. So going back to the original question, this tells me that 3 sine theta plus 4 cos theta can be expressed in the format 5 sine theta plus 0.93 radians to 2 decimal places. So we've expressed a sum of a sine function and a cosine function as a single sine function, which involves a translation and a stretch. Now, this isn't the only way of answering this question. I could have said 3 sine theta plus 4 cos theta was equivalent to r cos theta minus alpha. Now, in that case, the right-hand side would have expanded to give me r cos theta cos alpha plus r sine theta sine alpha. I can then continue the process by comparing coefficients working out everything in exactly the same way. I would get a different value of alpha, but that's okay because we're now writing this as a cosine function rather than a sine function. Remember, a cosine function and a sine function, they're essentially the same function, just one is a translation of the other. So reality is that we could actually have done this in a totally different way. And it would have resulted in a slightly different function, but you would find that when you drew the graph of this function, or when you drew the graph of your cosine function, you'd get exactly the same graph through the interchangeability of sine and cosine functions. Let's take a look at another example. We're going to express cos theta plus root 2 sine theta in the form r cos theta minus alpha. And we've got some conditions here on r and on alpha, and this time we're working in degrees. Now, cos theta plus root 2 sine theta is going to be expressed as r cos theta minus alpha. So let's use our compound angle identity to expand cos theta minus alpha. So that would be cos theta cos alpha plus sine theta sine alpha. Notice this has been very carefully chosen to include a negative sign here so that the expansion has a positive sign, which means that it matches the left-hand side very nicely. So there was a careful choice here. Now, both parts are multiplied by r as well. So let's compare coefficients. We want to compare coefficients and identify the value of r and the value of alpha. So I'm going to start by looking at cos theta first of all. Now on the left-hand side, we simply have a factor of 1 cos theta. On the right-hand side, we have r and cos alpha. Now, if we look at sine theta, on the left-hand side, we have root 2 sine theta. So that gives me a root 2. And on the right-hand side, we have r and sine alpha. Now, we know that if we square these and add them together, we get r squared. I don't have to write out the full working every time that we do this. If you want to, we can do. So 1 is equal to r squared cos squared alpha. 2 is equal to r squared sine squared alpha. And in a lot of these questions, it's essentially the same pattern each time of results. So adding these together, we get 3 is equal to r squared, and therefore r is equal to the square root of 3. Remember, r has got to be a positive value. So I can then substitute this back into either of these two results. It really doesn't matter which one we choose to sub back into. So I'm going to substitute into 1 equals r cos alpha. So that gives me cos alpha equals 1 over root 3, and I'm working in degrees. What do I get? Arc cos 1 over root 3 is 54.735, and I'll store that in a calculator memory, and we'll round that to 1 decimal place just for the moment. So now we can say that our original combination, cos theta plus root 2 sine theta, can be expressed as root 3 cos theta minus 54.7 degrees, with of course that angle given to 1 decimal place. Now the key thing here was a very clever choice of compound angle here. So if we'd chosen something else, it would have made the working a little bit more complex because the identity wouldn't have matched the left-hand side as well. So the careful choice here was noticing that we wanted a plus here between the terms, so we needed a compound angle formula that would have resulted in a plus here as well. Now the alternative would have been if we had cos theta plus root 2 sine theta equivalent to r sine theta plus alpha, because again on the right hand side when you expand this compound angle formula you'll end up with a plus. Now if you by mistake went with r sine theta minus alpha, it wouldn't be wrong, but you create more work for yourself and you have to deal with the negative signs. So the best way is to make sure that you match the left-hand side and the right-hand side clearly. So what can we now do with this question? Let's look at part 2. Hence find the maximum and the minimum values of this function and the smallest positive values of theta for which they occur. So we now know that cos theta plus root 2 sine theta is equivalent to root 3 cos theta minus 54.7, and of course that's a rounded angle. Now let's think about cosine, or the cosine function. The maximum value of cos anything is equal to 1, and the minimum value of cos of anything is equal to -1. So if we're finding the maximum value of the overall function, we can use the right-hand side to do this, because the maximum value is going to occur when cosine takes a value of 1, so the maximum value is equal to root 3. Similarly, the minimum value will occur when the cosine part is equal to -1, so that will give us negative root 3. Now, when do we get these values? So at the maximum value, we know that cos theta minus 54.7 degrees is equal to 1. So if we take arc cos, theta minus 54.7 degrees is equal to 0. So theta equals 54.7 degrees, 1 decimal place. Remember that we need to use the unrounded value of alpha in our calculations. Remember we stored it in a calculator memory? Now the minimum value is equal to negative root 3, and that occurs when cos, or the cosine part, is equal to -1. Now if we take arc cos, that gives me theta minus 54.7 ... is equal to 180 degrees. So add on 54.7 and we get to 234.73 ... which is 234.7 degrees to 1 decimal place. Remember to use the unrounded version of alpha. This will become really important, particularly when you work in radians as well. So now let's relate everything we've done back to transformations. So we know that this can be expressed as root 3 cos theta minus 54.7 degrees. So what transformations are taking place here if we were starting with y equals cos theta? Well, this part here represents a translation with a vector of 54.7 degrees and 0 units up or down. So 54.7 degrees to the right. And this part here, the root 3, represents stretch in the y direction, or parallel to the y-axis, with a scale factor of root 3. So you can see a sketch diagram of the function, and because it's a stretch with a scale factor of √3, you can see the peak and the trough of the graphs match √3 and negative √3 on the y-axis. Because there was a translation, we can see that this point here, which would originally have been at 0 for the traditional standard y equals cos x graph, is now at 54.7 degrees. This point here, which would have been at 90 degrees, is now going to be at 144.7 degrees. This point here would have been at 180, and it's now 234.7 degrees, so that corresponds with the minimum point of negative √3. And finally, this point here, which would have been 270, will now be at 324.7 degrees. So let's take a look at example 3. We need to state the maximum and minimum values of this function and the values of theta at which they occur. Now, you will hopefully have spotted that part of this denominator is the function that we have been dealing with. And we know that cos theta plus √2 sine theta can be expressed in the form √3 cos theta minus 54.7 degrees. So we can rewrite this function that we're now dealing with as y equals 1 over 4 plus √3 cos theta minus 54.7 degrees. So when is this function going to take its maximum value, and when is it going to take its minimum value? Well, the maximum value will occur when the denominator takes its smallest possible value. Because then you're dividing by the smallest possible value in the denominator, which will of course maximise the overall result. Now, that's going to happen when the green part, this part here, takes its lowest value, because there's nothing we can do about this 4 here, that's going to permanently be there. So all we can control is the green part. Now, that occurs when √3 cos theta minus 54.7 degrees takes its minimum value. And we know that that minimum value is negative √3. Now, we also know that this occurs when theta is equal to 234.7 degrees from the previous example. So the maximum value of the overall function is y equals 1 over 4 minus √3. Now the minimum value of the overall function occurs when the denominator is maximised. Because when you divide by a larger value, you end up with a smaller result. Now, this occurs when √3 cos theta minus 54.7 degrees takes its maximum value. Again, we can't control the size of 4, it's just there, so the only part we can control is the green part. So this takes its maximum value, which is √3. Now we know this occurs when theta equals 54.7 degrees to 1 decimal place, remember? Because of course you then end up with cos of 0, and cos of 0 is 1, so you end up with √3 multiplied by 1. So the minimum value of the overall reciprocal function is y equals 1 over 4 plus √3. So we make the denominator as large as possible. So let's have a look at a series of other examples. Now, we're going to express sine theta minus 3 cos theta in this format here. Now notice that there's a negative sign here, in the original function, which means we're using a compound angle formula that will expand to give us a negative as well. So the compound angle result chosen matches the original question very nicely. So sine theta minus 3 cos theta is going to be expressed as r sine theta minus alpha. So let's expand the right-hand side carefully. So we're going to use the compound angle formula for sine theta minus alpha, which is, of course, sine theta cos alpha minus cos theta sine alpha. And both parts, of course, are multiplied by r. Now, compare coefficients, look at sine theta on both sides, and also please make sure you look carefully at cos theta on both sides as well, and look at the coefficients. So let's start off by comparing the coefficients for sine theta. Now, on the left-hand side, we have 1 sine theta, and on the right-hand side, we have r cos theta as the multipliers of sine theta. So what else do we now do? Let's look at cos theta. So on the left-hand side, we have a 3. And because the identity that we are using was very carefully chosen, we don't have to worry about this negative here because it's accounted for. There's a negative here and there's a negative which matches here. So we no longer have to worry about the negative on either side. We can just look at the coefficients. So we have 3 on the left-hand side, and on the right-hand side, cos theta is multiplied by r sine alpha. Now, we know that we've got to square both of these, or we can square both of these as a way forward. So we know that 1 is equal to r squared cos squared alpha, 9 is equal to r squared sine squared alpha, and we're going to add these together, which gives us 10 equals r squared. So r is equal to the square root of 10. Remember that we choose a positive value for r, for simplicity. The whole thing can be done with a negative value of r, but we create a more complex question when we do that. So we now need to find our value of alpha. So I'm going to substitute back into the pink equation. It doesn't actually matter which one we substitute back into. 1 equals r cos alpha. So 1 equals root 10 cos alpha. So cos alpha equals 1 over root 10, which gives us alpha equals. So alpha then equals 71.565 ... degrees. Remember, from the original question, it's clear we're working in degrees. So 71.6 degrees to 1 decimal place. Now, we must answer the final question because remember we were asked to express sine theta minus 3 cos theta in this format. So we do need to go back and actually set out the full final answer. So sine theta minus 3 cos theta can be expressed as root 10 sine theta minus 71.6 degrees, and that of course is rounded to 1 decimal place. Now there's a secondary part to this question. We are going to now solve the equation sine theta minus 3 cos theta equals 1. Now, this is the beauty of having expressed our trigonometric function as a single sine function. Now, one thing I would warn about is you need to use the full answer, not the rounded answer, when we're doing these calculations. So please make sure you've got the answer of 71.565, etc. stored in a calculator memory ready to use. So first step is to divide by root 10. So sine theta minus 71.6 is 1 over root 10. And then we need to use arc sine, which gives us the values of 71.6 degrees. So theta minus 71.6 is equal to 18.4349 ... I'm now going to sketch the sine curve. So here is my graph of, very simply, y equals sine x, and I'm going to draw a horizontal line across the graph which represents 1 over root 10. So this line here is y equals 1 over root 10, and there is an intersection here which is the angle 18.43 degrees, and then there is another intersection over here which, if we use the symmetry of the graph, we can see this gap here is the same as this gap here. So this value is 180 minus 18.43 degrees. Now, in both cases, we're not finding values of theta, we're finding values of theta minus 71.6. So far, we've got theta minus 71.6 equals 18.43, dot, dot, dot. And we have theta minus 71.6 is equal to 180 minus 18.43. And in both cases, we need to then work out the values of theta that we get. So this one gives me 89.998 dot, dot, dot. And this one gives me 233.129 dot, dot, dot. Now, please remember, as I keep saying, you need to use the full answer for the 71.6 degrees, not the rounded answer. If you round mid-calculation, your final answer may not be fully accurate. So you've got to use the full level of accuracy, either stored in a calculator memory or write down 4 or 5 decimal places so you've got a good level of accuracy to actually use. So our final answers for theta are going to be 90.0 degrees and 233.1 degrees, both rounded to 1 decimal place. So the last example, we're working in radians this time. Again, notice the negative sign here in the original function, and this is matched by the correct identity. So 2 sine theta minus 3 cos theta, we're expressing it in the format r sine theta minus alpha. Let's expand the right-hand side using our knowledge of the compound angle formula. Sine theta cos alpha minus cos theta sine alpha. So again, you can see the negative here is matched by the negative here, which makes comparing coefficients so much easier. Don't forget there was an r here, so both parts here need to be multiplied by r as well. Now, let's compare our coefficients. So we've got sine theta here and here. So if we look at sine theta, what does that tell us? It tells us that 2 on the left-hand side is matched by r cos alpha. And then if we look at cos theta here, it's matched by cos theta on the right-hand side. So on the left-hand side, we have a 3. Again, we can ignore the negative sign because there's 1 on both sides, so they would simply cancel. So 3 on the left-hand side is matched by r sine alpha. Now, we can square both, so we get 4 equals r squared cos squared alpha. 9 equals r squared sine squared alpha, and then we can add both of these results together. Notice we could actually, if we wanted to, find alpha first. It is a distinct possibility if you divide the sine equation by the cosine equation. So if I call this equation 1 and equation 2, we could do equation 2 divided by equation 1, which would give us 3 over 2 equals tan alpha. So you can find alpha and then substitute back to find r. It is an alternative approach which is perfectly valid mathematically, one to consider as an alternative way of doing things. I'm going to take the equations that we've found here, equation 1 squared and equation 2 squared, and I'm going to add them together. So we get 13 equals r squared. So r is equal to the square root of 13. Now I'm going to substitute back into one of my equations. I'll pick equation 1. So that then gives me 2 equals root 13 cos alpha. So cos alpha equals 2 over root 13. Remember, we are working in radians. We know that from the question, so you must double check that you are doing that correctly. And this gives us alpha equals 0.98279 ... which I'm going to store in a calculator memory for further use, and we can round that to 0.983 radians to 3 significant figures. Now don't forget, we haven't actually finished the question until we express the original trig function in its new format. So remember, 2 sine theta minus 3 cos theta can now be expressed as the square root of 13 sine theta minus 0.983. So there's a secondary part to this. We've got to write down the greatest and least possible values of this function here. Now notice the second part of this function, well, the second and third terms of this, are of course what we now know as root 13 sine theta minus 0.983 radians. So overall, if this is a function of theta, this is f of theta, all of this, we can say that f of theta is equal to 1, and instead of plus 2 sine theta minus 3 cos theta, we can say that f of theta is 1 plus root 13 sine theta minus 0.983. Now, when does this take its maximum or greatest value? Well, remember, the only part of this that we have any control over is the trigonometric part, because the 1 will always be there. So if we want to maximise f of theta, we need to maximise the sine part, which takes a maximum value of 1, which means overall a maximum value of root 13, which means the maximum value of f of theta is equal to 1 plus the square root of 13. Now, what about the minimum value of f of theta? Well, that will occur when the sine part, so specifically this part here, takes a value of negative 1. So this overall takes a value of negative root 13. So f of theta's minimum value is 1 minus root 13.